So, having used the curve profile scanning tool to create this point cloud, what are we going to do with that data? Well, the most convenient way of using that data, I think, is to import a DXF file so that we can compare the data to the CAD profile and see how close it is to the nominal profile. Profile projector users would relate to this in terms of an overlay, the transparency that you would actually place onto the optical comparator to try and find a fit between the projected image and your drawn image. The DXF is basically an electronic version of that. So let's bring in a DXF of that shape. I've found the file. I'm going to import that file as a curve profile. We can use DXFs for other purposes, which I'll cover in other clips. So we're going to bring this in as a metric DXF. I'm going to apply a 0.2 tolerance band as a general tolerance band to this DXF, which I can edit later. And let's bring in the DXF, and you can see here the initial position is slightly off from the measured position. So we need to do some manipulation. Just like you would do with the profile projector, you'd manually move that overlay chart around to try and visually align that with the image. We can do that also using these controls. So I'm going to jog the DXF to the left, to the right, up and down, and I can also rotate it. But clearly what I want to happen is for the software to calculate the best fit. So by pressing the start button there, the software does a calculation and has mathematically fitted the DXF so that the profile error is actually minimized. This is the best profile error. And you can see that all of my data points now have gone green and are showing as very close to the nominal line. So visually, I can immediately see that all of those green data points mean that every one of those 2.5 or something thousand data points are within the 0.2 tolerance band that I imported with the DXF. So that is a visual equivalent of the profile projector overlay. Okay, so having brought the DXF in and made a best fit calculation, we get this visual report that all points are in tolerance. That's great. The problem with camera-based systems in the past has been the limited field of view means that we can't see what that overlay and image fit looks like. The big advantage with the latest generation of Fusion software is that we can stitch our images together. This is my current camera view, but if I roll out on the mouse and zoom out here, we can see that actually I have a picture of the entire part that I've measured, because every time we've been to a position, we've saved that image and connected them all together, stitched them all together to give us a larger saved image. Now, on top of that image, I can use this feature, overlays, to show other information on top of the stitched image. If I select DXF, you can see I can bring in the DXF here, and I can see that all of the features now fall within my tolerance band. So this is the view that we're used to seeing on a 500mm screen profile projector, and now for the first time we can actually replicate that on a camera-based vision system. So now we have a visual graphical display showing our points, our scanned data points, as green and in tolerance. We also have a visual overlay of the DXF placed over the top of the stitched image. So anything, even if we haven't measured the feature, we can still see where it appears in relation to the DXF. But the final thing that a software-based system like this can give you is an actual result. If we want to, we can dimension that profile and actually put a number on it. And that's the massive difference between this subjective view that you have to take with a profile projector and using this method where we can automate the process, we can visually see all of the things that the operator is used to seeing, but at the end of the day we have a number that we can report. We have empirical data that we can report, we can tolerance, and we can plot trends. That's where the industry needs to be going. So the process that we've just been through, using video edge detection tools to automatically find the edge of features. We've taken lots of data points to describe all these features. We've created a drawing. We've dimensioned the part. We've done some scanning and best fitting to DXFs. At the end of the process, we've generated a report, but the real value in the system is that it's a CNC system. So if I hit the play button now, you'll see that the software has actually remembered everything that I've done. We've got a program to measure this part now, and that is what we call the teach and repeat programming style of this software. I'm not actually having to program anything. I haven't touched the keyboard yet this morning, yet we've created drawings and reports and we're measuring a part automatically.